Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the paper 4 exam for May-June 2019 variant 1. So let's get started. Question 1 says a rocket is stationary on the launch pad at time t equals 0. The rocket engines are switched on and exhaust gases are ejected from the nozzles of the engines. The rocket accelerates upwards. Figure 1.1 shows how the acceleration of the rocket varies between time t equals 0 and time t equals tf. We have first accelerating with increasing rate or increasing acceleration. Then we have constant acceleration on the graph. Part A says first define the acceleration. It is the rate of change of velocity or velocity changed per unit time. Part B says on figure 1.2 sketch a graph to show how the speed of the rocket varies with time between time t equals 0 and time t final. So we had a section of the graph where the acceleration changed behavior from increasing acceleration to constant acceleration, and we started from rest, so we started from speed 0, and acceleration started from 0 from the above graph. So we start with gradient equals 0 and then gradient increasing until we reach a constant gradient, which means a constant straight line or a straight line with constant slope. So first we have a curve with increasing gradient like this, for example, and from this part we draw a straight line with the same gradient as the one we finished with, the curved part. So this transition must be smooth. So it looks like this. Part C says sometime later the rocket is far from Earth. The effect of the Earth's gravity on the motion of the rocket is insignificant. As the rocket accelerates, its momentum increases. State the principle of conservation of momentum. First, we say that the total momentum of a system remains constant, or the initial total momentum of a system is equal to the final total momentum of the system if there are no external forces acting on it, since a force would cause a change in momentum. Part II says explain how the principle of conservation of momentum applies to the accelerating rocket and the exhaust gases. We can say that the change in momentum of the rocket is equal and opposite to the change in momentum of the gases. So if we have equal and opposite magnitudes, they cancel each other, so the total change is 0, or we say that the total momentum of the rocket and gases before ignition is equal to the total momentum of the rocket and gases after ignition. Question 2 says figure 2.1 shows a sign that extends over a road. We have the sign with the unknown weight here and the distance from the center of the pole 1.8 meters, and there is a point P at a distance of 1.3 from the center, and there is a concrete block at a distance of 70 centimeters, not meters, from the center of the pole. The mass of the sign is 3.4 times 10 to the power of 3 kilograms. Calculate the weight of the sign. So weight is equal to mg, so we multiply 3.4 times 10 to the power of 3 times 9.8. That gives an answer of 33,320. That is in newtons, or we can approximate that to 3.3 times 10 to the power of 4 newtons. Part B says the weight of the sign acts at a horizontal distance of 1.8 meters from the center of the support post, and it produces a turning effect about point P. Point P is a horizontal distance of 1.3 meters from the center of the support post. Calculate the moment about P due to the weight. So if point P is here and the center is here, this distance is 1.3 and the weight is acting at a distance from the center of the pole 1.8, but we need the distance between the force and the pivot, or the point P. So this distance is equal to the subtraction 1.8 minus 1.3. So first we write down the equation for moment, force times perpendicular distance. The force is 33,320 and the distance is 1.8 minus 1.3. That gives an answer of 16,660. So it's approximately 17,000, or 1.7 times 10 to the power of 4 Newton meter. II says a concrete block is positioned on the other side of the support post with its center of mass a horizontal distance 70 centimeters from the center of the support post. State what is meant by the center of mass. It is the point in an object where the mass is assumed to be concentrated, or the weight is assumed to be acting. Part 2 says the weight of the concrete block produces a moment about point P that exactly cancels the moment caused by the weight W. Calculate the weight of the concrete block. So about point P as a pivot, we have this distance, the difference between 1.8 and 1.3, that is 0.5, or we already calculated the clockwise moment of the weight. As for the concrete block, the distance is 70 centimeters, which is 0.7 meters, plus this distance, which is 1.3. So the total distance here is 2.0 meters, and we have an unknown force. Using the principle of moments, clockwise moments equal to the anti-clockwise moments, we can say that 16,600, the already calculated moment of the weight, is equal to the clockwise moment, which is equal to the force, the weight of the block, multiplied by the distance 2.0 meters, and then we divide by 2 on the left side. That gives an answer of 8,330, so it's approximately 8.3 times 10 to the power of 3 newtons. Part C says the concrete block is removed, the sign and support posts rotate about the point P in a clockwise direction. State and explain what happens to the moment about point P due to the weight of the sign as it rotates. In order for you to imagine that, I'm going to draw the sign, and then I'm going to draw the sign with its tilt clockwise. So for example, it will look like this, and this is a point P, this is a point P. The weight was at a distance of 0.5 meters, but now point P is further away from the point of the center mass of the sign, so the distance actually increased. So as distance increases, the moment of the weight will also increase. So we say that the center of mass and the weight of the sign go further from P, so as distance increases, the moment also increases. Question 3 says a cube of side 0.040 meter is floating in a container of liquid. Figure 3.1 shows the surface of the liquid is 0.028 meters above the level of the bottom face of the cube. The pressure of the air above the cube exerts a force on the top face of the cube, and the valve is closed, so everything is at rest. Part A says explain in terms of air molecules how the force due to the pressure of the air is produced. First, we say that air molecules move randomly and collide with the surface, and then we say that the change in momentum as they rebound exerts a force over the area of the surface or of the cube. Part B says the density of the liquid in the container is 1,500 kilograms per meter cubed. Calculate the pressure due to the liquid at a depth of 0.028 meters. We use pressure is equal to rho GH, and then we substitute 1,500 times 9.8 multiplied by 0.028 gives an answer of 411.6. We can approximate that to 410 Pascal. Double I says calculate the force on the bottom face of the cube caused by the pressure due to the liquid. So the force is equal to pressure multiplied by area. We substitute 411.6 multiplied by the area of a cube is the square of one side. So we calculate 0.04 squared. That gives an answer of 0.65856 approximately. We can do a further approximation to make it 0.66 newtons. Or we can approximate it to 3 significant figures to make it 0.659. Part C says the valve is opened and liquid is pumped into the container. The surface of the liquid rises a distance of 0.034 meters. The cube remains floating in the liquid with its bottom face at 0.028 meters below the surface of the liquid. Calculate the work done on the cube by the force in B double I. So we use work equal force multiplied by the distance, and the force was equal to 0.65856. Then we multiply that by 0.034. The answer here is 0.02239, which we can approximate to 0.022, and the unit for work is joule. Part double I says suggest one reason why this is not an efficient method of lifting up the cube. It must be due to some form of energy losses. So we can say that friction between the liquid and the tube or the pipe wastes a lot of energy. So since energy is wasted, that means that a large fraction of the input will not be transferred as an output. Question 4 says gas of mass 0.23 gram is trapped in a cylinder by a piston. The gas is at atmospheric pressure, which is 1.0 times 10 to the power of 5 Pascal. Figure 4.1 shows the piston held in position by a catch. The volume of the trapped gas is 1.9 times 10 to the power negative 4 meters cubed. An electrical heater is used to increase the temperature of the trapped gas by 550 degrees Celsius. Part A says the specific heat capacity of the gas is 0.72 joules per gram degree Celsius. Calculate the energy required to increase the temperature of the trapped gas by 550 degrees. We can use Q is equal to mc delta theta, and the mass was 0.23 in grams, but since the specific heat capacity is also in grams, we do not need to convert it. So multiplied by 0.72 and then by the change in temperature 550, that gives an answer of 91.08. We can approximate that to 91 joules. Part I says the power of the heater is 2.4 watts. Calculate how long it takes for the heater to supply the energy calculated in AI. Power is equal to energy divided by time. Therefore, time is equal to energy divided by power. We divide 91.08 over the power, which is 2.4, to get an answer of 37.95, which is approximately 38 seconds. Part 2 says, in practice, it takes much longer to increase the temperature of the gas by 550 degrees Celsius using the heater. Suggest one reason for this. The reason is some form of heat losses. We can say that some energy or heat energy is lost to the surroundings of the room, or we can say that some energy is used to heat the roof or the floors of the room. Question B says, when the temperature of the gas has increased by 550 degrees Celsius, its pressure is 2.9 times 10 to the power 5 Pascal. The catch is then released, allowing the piston to move. As the piston moves, the temperature of the gas remains constant. First, it says, state and explain what happens to the piston. We say that the pressure inside is greater than the pressure outside, so there is a resultant force that pushes the piston outwards towards the lower pressure. I says, determine the volume of the gas when the piston stops moving. We can use P1 V1 is equal to P2 V2 or PV equal constant. The initial pressure here is 2.9 times 10 to the power of 5, and the volume from the previous page was 1.9 times 10 to the power of negative 4. After the piston stops moving, the pressure will return to atmospheric pressure, which was 1.0 times 10 to the power of 5 from the previous page. And then we have only one unknown, which is V2. We divide the left-hand side by 1 times 10 to the power of 5 to get the volume. It is equal to 5.51 or 5.5 times 10 to the power of negative 4 meters cubed. Question 5 says, liquids and gases are two states of matter. Part A says, in both boiling and evaporation, a liquid changes into a gas. Part I says, state two ways in which boiling differs from evaporation. We can start by saying that boiling occurs at a certain temperature and evaporation occurs at any temperature. The second difference is that boiling occurs through the whole of the liquid or through the whole liquid, but evaporation occurs only at the surface of the liquid. I says, before injecting a patient, a doctor wipes a small amount of a volatile liquid onto the patient's skin. Explain in terms of molecules how this procedure cools the patient's skin. We start by saying that volatile liquids evaporate rapidly or quickly, and to change from liquid to gas, molecules absorb energy from the skin to break intermolecular forces, leaving the skin or the skin molecules with lower average kinetic energy, since kinetic energy is the measure of temperature, or the temperature is the measure of the average kinetic energy of molecules. Kinetic energy decreases, so temperature decreases. Part B says, gases can be compressed, but liquids are incompressible. Explain in terms of molecules why liquids are incompressible. We say that molecules are already very close to each other in liquids and have very strong forces between them. So you cannot compress them unless you have a very large force or a very large amount of energy. Question 6 says, green light of frequency 5.7 times 10 to the power of 14 Hz is traveling in air at a speed of 3.0 times 10 to the power of 8 meters per second. The light is incident on the surface of a transparent solid. Figure 6.1 shows the wavefronts and the direction of travel of the light in the air. The light travels more slowly in the transparent solid. Explain in terms of the wavefronts why the light changes direction as it enters the solid. You may draw on figure 6.1 as part of your answer. We do not need to draw. We just say that a part of the wavefront enters the solid and slows down before the rest. So part of the wavefront moves slower, causing it to bend, because part of the wavefront is moving with a high speed and the other part is moving with a low speed. So this travels a long distance, this travels a shorter distance. So the bending happens at the boundary between the two media. Part B says the refractive index of the transparent solid is 1.3. Part I says the light is incident on the surface of the solid at an angle of incidence 67 degrees. Calculate the angle of refraction of the light in the solid. We use the equation of refractive index. It is equal to sine the angle in air divided by sine the angle in the other medium. Substituting with the 1.3 equal to sine the angle in air 67 divided by sine the unknown angle of refraction r. We replace sine r with 1.3, and after calculating sine 67 over 1.3 and getting the answer, we do an inverse sine, so shift sine answer. That gives an angle of 45.078966. We can approximate that to 45 degrees to two significant figures. Double I says determine the wavelength of the green light in the transparent solid. We need the speed and the frequency to get the wavelength, but we do not have the speed. We can also use another equation for the refractive index. It is equal to the speed of light in air divided by the speed of light in the medium. So the speed of light in the medium or in the solid is equal to 3 times 10 to the power of 8, which is the speed of light in air, divided by the refractive index 1.3. And then we say wavelength is equal to the speed divided by the frequency. So we have the fraction from the above calculation. Using the exact value, we divide by the frequency given at the first page. We have 5.7 times 10 to the power of 14. This whole calculation gives us a wavelength of 4.04858 times 10 to the power of negative 7. We can approximate that to 4.0 times 10 to the power of negative 7, and the unit here for wavelength is meters. Question 7 says figure 7.1 shows a circuit diagram that includes component X. State the name of component X. This is a thermistor, which depends on the temperature of the environment or its own temperature. Part B says the electromotive force of the battery is E. The switch is closed. The potential difference across the 30 ohm resistor is V30. The potential difference across the 20 ohm resistor is V20. The potential difference across component X is Vx. State an equation that relates Vx with V30 and Vx with E and V20. First, we label the symbols on the diagram. So this is E, this is Vx across this one. There is V30 across this one and V20 across this one. First, the parallel connection between X and the 30 ohm resistor makes the voltage the same. So Vx and V30 are equal. We write it as Vx is equal to V30. And as for the series connection between this section and the 20 ohm resistor, the voltage of this part together and this part added will be equal to the EMF of the battery. So E is equal to Vx plus V20 or V30 plus V20. But since we are required to relate Vx and E and V20, we write that E is equal to Vx plus V20 or Vx is equal to E minus V20. Part C says the EMF of the battery is 6.0 volts and the resistance of component X is 15 ohms. Calculate first the total resistance of the circuit. We had 15 ohms in parallel with 30 ohms, and these two were connected in series with a 20 ohm resistor. So this is the total connection. First, we calculate the parallel part as 15 times 30 divided by 15 plus 30. Then we add that to the 20 ohm resistor to get the total resistance of the circuit in series. This gives a total of 30 ohms for the whole circuit. Double I requires the ammeter reading. The current in the ammeter is actually the total current in the circuit. So we use total voltage and total resistance. For the total voltage, we have 6.0 volts and the total resistance is 30 ohms. This gives an answer of 0.2 amperes or 0.20 amperes. Question D says the temperature of component X increases. State and explain what happens to the ammeter reading. We start by saying that the resistance of X, or the thermistor, decreases, so the total resistance also decreases, and current is inversely proportional to resistance, so the reading or the current increases in the circuit. Question 8 says a student turns the handle of an alternating current generator and the coil rotates. Figure 8.1 represents the structure of the AC generator. There is an alternating voltage output between the two terminals. Explain why rotating the coil produces an output voltage. In the first place, we say that the coil cuts the magnetic field of the magnet, which induces an EMF in the coil. Or we can say that there is a change in flux in the coil as it rotates, and this induces an EMF in the coil. Double I says state the position of the rotating coil when the alternating output voltage is at the maximum value and explain why the maximum output occurs at this position. So this happens when the area of the coil is horizontal or parallel to the field, because the rate of cutting the field at this position is maximum. So if the magnetic field is pointing in this direction and the coil is flat like this, horizontal, the lines at the edges of the coil will be moving at right angles to the field, so they cut the field with maximum rate. Part B says a lamp and an open switch are connected in series to the output terminals of the AC generator. The switch is closed and the lamp lights up. The student has to apply a greater force once there is a current in the coil on the handle. So explain why a greater force is needed to keep the lamp lit. This is about Lenz's law. We say that as there is a closed circuit now, an induced current flows in the coil. This current opposes the motion or creates a force that opposes the motion. So an extra force is needed to keep the motion with the same speed. Question 9a says figure 9.1 shows a beam of alpha particles moving towards a thin sheet of gold in a vacuum. Detectors in the region surrounding the thin gold sheet detect alpha particles and determine the number of particles that travel in various directions. State and explain what can be deduced from the following observations. I says the majority of the alpha particles pass through the gold sheet undeflected and are detected on the far side. We say that most of the atom is empty space because most of the alpha particles miss or do not hit the nucleus or the core of the atom. So most of them go undeflected because the nucleus is very small. We can also say in the deduction that the nucleus is very small or is tiny. Double I says a small number of alpha particles are deflected as they pass through the gold sheet. That means that they were repelled. This shows that there is a positive or positively charged core inside the empty space. And this is because alpha particles are positively charged and they were repelled. So there must be a like charge inside that. Triple I says a very small number of alpha particles are deflected through very large angles or return back the way they came. We say that the nucleus is very heavy or contains most of the atom's mass because the alpha particles that hit the nucleus rebounded. So they could not have rebounded if they hit a lighter mass or an approximately equal mass. They will just keep moving in the same direction and the object will be knocked out of the way. But if the mass of the object that you hit is much greater than your own mass, you will rebound backwards. Question B says a beam that consists of both alpha particles and beta particles is passed through a region of space where there is a magnetic field perpendicular to the direction of the beam. State two ways in which the deflection of the alpha particles differs from that of the beta particles. We start by saying opposite directions because they have opposite charges and create opposite currents. And using Fleming's left-hand rule, you will find that for the same direction of magnetic field and opposite direction of current, there is an opposite direction of force, so opposite deflections. And as for the amount of deflection, we say that a deflection of beta particles is much greater than that of alpha particles because beta particles are much lighter and they will be affected greatly by the same force. So this was the end of the exam. I hope you enjoyed this video and found it useful. If you did, please give it a thumbs up and subscribe to the channel, and I will see you in another video.